Hello students, welcome to Apna Tutor channel. So in today's lecture, we'll be doing some NCERT exercise questions of chapter 1. So the question number 1 is, what is the force between two small charged spheres having charges of this and this placed 30 centimeter apart in air? So we are having two charged spheres and they are at some distance 30 centimeter from each other. So I have told you that if the charge separation is comparably large, so the force which will be applying will be for the point charges, that is Coulomb's law. Okay, so the Coulomb's law states that force is equal to k q1 q2 upon r square, right? So you will be substituting the value of k, that is 9 into 10 raised to power 9, and q1 q2 value you can write from the here, and distance also you are given. So you can solve this question, try it by yourself. So let's read the second question. It says that electrostatic force on the small sphere of charge 0.4 microcoulomb due to another small sphere of charge minus 0.8 microcoulomb. So a small sphere has a positive charge of 0.4 and another we have small sphere of negative charge, that is 0.8. So the force between them is 0.2 newtons. Now we have to calculate the distance between the two spheres. Again we can apply this relation that force is equal to, we have studied that Coulomb's law is applicable for both attractive and repulsive charges, right? So we are given this formula. Now we'll be substituting the value of force and both the charges, and from there you can find the distance. Okay, and then the second part is, what is the force on the second sphere due to the first sphere? So let's say this is the first sphere and this is the second sphere, right? Now we have to calculate what is the force on the second sphere. Force on 2 due to 1. So this force will be same as 0.2 Newton, which is given in the question. Since we know that two charges attract equal and opposite to each other. Okay, so you can substitute the values and try it by yourself. Just keep in mind that here you have to note that the units. Okay, so it is in microcoulomb, so you have to write it in terms of coulombs, and that will be 10 raised to power minus 6, right? So the things you have to keep in mind in these two questions is your SI units, that is everything is in SI unit. Okay, since in the first question it is given in centimeters distance. Okay, and second thing you have to keep in mind whether it is in the medium is air or something else. Okay, for medium air you can keep it 1 by 4 pi epsilon naught, but if it is not air you have to change accordingly. Okay, let's read the third question now. Check that the ratio k e square by g m e m p is dimensionless. Look up at the table of physical constants and determine the value of this ratio. What does this ratio signify? So we are given the ratio where we are able to understand that it is the ratio of electrostatic force upon gravitational force, right? Now let us first check that this ratio is dimensionless or not. For that we need to put the values of this dimensions of all the quantities. So E is the charge, so for the charge we can write it to be a t square. Okay, since there are two charges and we know that I is equal to charge upon time. So it will be A into T, right? So let's check the dimensions of K and G, and we know the dimensions of mass is m square. Okay, so let us find the dimensions of K and G. So for the K, we know that K will be equal to force into r square upon q square. So it will be, and we know the dimensional formula of force is m l t minus 2, right? And r square is l square upon charge square. Again we'll write a square t square. Okay, so we are given this, so we can substitute it over here. And similarly we can find for the G. So we know gravitational forces G m1 m2 upon r square. For G we can write force to be again m l t minus 2, and it will be l square, so it will be cube upon m square. So we are given this. Now let's substitute all the values over here and check whether the ratio is dimensionless or not. So let's substitute all the values for this ratio. So we are given ke square by GMEMP. Okay, so for the k we have just calculated, it is m l cube t minus 4 and a minus 2. So again we can substitute for e, it is a square t square, right? Now for g we have calculated m minus 1 l cube t minus 2, right, into m square, right? So we can cancel some of the terms. We can see that a square is getting cancelled and l cube is cancelled, and it will be t is also getting cancelled from here. So I think we are left with this. Again it will become reciprocate and it will be m square, so it will be cancelled with this. So this quantity or this ratio is dimensionless, right? So now let's move to the next part where it is said that we have to determine the value of this ratio. So for this ratio, now let's put the values of k, which is equal to 9 into 10 raised to power 9, and e also we know that it is 1.6 into 10 raised to power minus 19 coulomb upon, we have this g equals to 6.67 into 10 raised to power minus 11, and mass of electron and proton we know, for the electron 9.1 into 10 raised to power minus 31, and you have to now substitute all the values of, okay, so mass of proton also you have to substitute. So you will get to know that the ratio is approximately equal to 10 raised to power 39 times. Electrostatic force ratio is equal to 10 raised to power 39 times gravitational force, which shows that or signifies that electrostatic force is highly greater than or stronger than gravitational force. Okay, so this is the significance of this ratio. Now let's move on to the next question, which says that explain the meaning of the statement electric charge of the body is quantized. So I have told you this in very first lecture. This meaning, it means that the total charge on the body is equal to the integer multiple of the elementary charge. So suppose if I have the charge on the body that is equal to, we have seen in our first lecture, right? So it is equal to q equals to ne. where n is equal to plus minus 1, plus minus 2, and so on, right? So we can say that the amount of charge transferred is based on the integer multiple. There cannot be in it like 2.5 or 0.5. In such a way we can't have our electric charge. Okay, so the next statement is, why can one ignore the quantization of electric charge when dealing with macroscopic large scale charge? So what does it mean? Why we can ignore this quantization when we are dealing with the macroscopic charges? Suppose if I need to give you some example, uh, let's first understand mathematically so that you can understand physical significance easily. We know this formula, right? Q equals to Ne, and since we are dealing with the macroscopic large number of charges, so let the number of charges be of the order of 10 raised to power 20, 30. Okay, so we'll have the expression Q upon E equals to N, where this is a very large number, while this will be of the order of 1.6 into 10 raised to power minus 19, right? So this will be very small value. That's why we can ignore it. So this was the mathematical meaning. But what does it mean physically? You can understand in a very simple way. Suppose you have a water pipe. Okay, so when the water is flowing from the pipe, so that is the amount of water which is flowing continuously. So that water is flowing in large amount, and we can't see a single water droplet. We have to see the whole amount of water passing through the pipe. But as we close the tap, then the amount of water decreases. So a stage will come when we'll see drops of water. So that drop will, then we'll not consider it to be the macroscopic scale. Okay, so this is the analogous meaning. So you can understand, like in our daily life we are dealing with the everyday circuits or the bulk materials, where the total charges passing through the circuit is very much large. So there we can ignore this quantization to some extent, right? Now the next question is, when a glass rod is rubbed with silk cloth, charges appear on both. A similar phenomena is observed with many other pairs of the bodies. Explain how this observation is consistent with the law of conservation of charge. So this also I have told you in first lecture, that amount of charge lost by one body is equal to the amount of charge gained by that another body, which shows the conservation of charge, right? So we can say that the amount of charge on the two bodies is exactly same in order to keep the total charge before rubbing equals to total charge after rubbing, since the charge before rubbing on the two bodies was zero. So when the either we have seen, we have number of methods. Okay, method of charging, in that we have studied charging by friction. So by rubbing we can see that one of the body gets positively charged. Here glass rod will be getting positive charge, while the silk cloth will be getting same amount of negative charge. So then we can say that the total charge will be same before and after, which shows that it is consistent with the law of conservation of charge, right? So let's move to the next question, which says that, so now we have 4-point charges, and the charges are given A, B, C, D, are located at the corners of the square. So let us draw the diagram over here. Let us say this is a square. Okay, so square, and it has 4 corners A, B, C, D, and each corner is having this charge. So QA is having 2 microcoulomb and QB this much charge. Similarly, these are the charges. So plus 2, minus 5, and it is plus 2 again, and again we have is minus 5. So these are the charges are located of at the corners of the square of side 10 centimeter. So each side is 10 centimeter, right? Now what is the force on the charge 1 microcoulomb which is placed at the center of the square? So we are placing a charge of 1 microcoulomb at the center, and you have to calculate force on this charge. So we'll be calculating force on this charge due to the all other charges. First we'll calculate force on this. Let me say that center charge is O, since we have C already present. Okay, so force on, first we'll calculate force on O due to A, then we'll calculate force on O due to B. So since this is we'll also see the direction. This is the positive charge, so force will be in this direction, and we'll calculate force on O due to B, that will be in this direction. Okay, and then we'll calculate force on O due to C, so it will be away from it, right? And then we'll find force on O due to D charge. So since it has a negative sign, so it will be towards it, that is attractive nature. So we can say that in both the sides the amount of charge is same, and hence they will be cancelled out. So the forces will be equal in magnitude and opposite in directions. Hence we can say that the net force on this 1 microcoulomb charge placed at the center of the square will be 0. So this force will be 0. If you want to calculate for each, you can try it. You will get the same answer. So let's move to the next question, which says that an electrostatic field line is a continuous curve. That is, a field line cannot have sudden breaks. Why not? So we have to explain this, that electric field lines are continuous in nature, they can't break. So generally we talk about the field to be, or we imagine the field to be imaginary. Okay, sorry, continuous. Okay, so if we say the field lines, so they are continuous in nature. Suppose if we have a positive charge and here we are having a negative charge, so the field lines which are moving from the positive charge to the negative charge all over the region, they are continuous in nature, they cannot have a break or due to anything. Also, if we need to see by mathematical expression, we can say that force is, or field lines is equal to force upon unit charge. So here we have no expression which is dealing with the sudden break, so we can say that the field lines are continuous in nature. So if you want to write, you can write it in this way, that electric field is inversely proportional to r square. And this expression also shows that the electric field decreases gradually as we are increasing in distance. So there is a gradual decrease, and there will be nothing that can cause sudden breaks or uh, jumps. Okay, so let's move to next question. Explain why two field lines never cross each other at any point. So if two electric field lines crossed each other, suppose we have electric field, one of the line is this and then we have this, so if they are crossing, so we'll have two directions of the field lines, right, which is not possible. So at the point of intersection there are two directions of the electric field lines, therefore we can say that they should never intersect. Now let's move to the next question, which says that 2 point charges, so we are having a qa charge and a qb charge, they are located at 20 centimeter apart in vacuum. Okay, now what is the electric field at the midpoint? So we are having a configuration, let it be point A and let it be point B, and the distance is 20 centimeter. So what is the electric field at the midpoint of the line OB joining the two charges. So you have to find the electric field. So let me draw it in a big broader way. So this is QA charge and this is QB charge, and here at the midpoint we have to find the electric field. Okay, so we have positive 3 microcoulomb charge on the A point and minus on the B point. So if we have to find the electric field, let's see the direction of the electric field first. So that for the positive charge, electric field will be away from the charge, so it will be in this direction, and for B it will be in again this direction only, it will be towards it only. Okay, so you can calculate and you can add up for, so the net electric field will be electric field due to A and electric field due to B. So first of all you can calculate its magnitude, which will be kq by r square, and now r will be this much of the distance. So the total distance was 20, but we will take here 10 centimeter, and of course you have to convert its unit to meters. You have to write everything in SI units, right? So then you can add both and you can get the answer. Now if a negative test charge of the magnitude 1.5 into 10 raised to power minus 9 is placed at this point, what is the force experienced by the test charge? Now we are placing the point test charge, and that is negative test charge, right, at point A. So let it be Q naught, which we are placing at O point. Okay, so we have to find the force experienced on that charge. Now force, we know that it is equal to Q naught into E. So we are given the test charge value equal to 1.5 into 10 raised to minus 9 coulomb, and we have calculated electric field in the above part A. So we can substitute its value whatever we get, and then we'll get the desired value of force, right? So now let's move to the next question, which says that a system has two charges QA and QB. Now the charges are equal in magnitude but opposite in sign. Okay, are located at the point this and this respectively. What are the total charge and the electric dipole moment of the system? Now you have to calculate the total charge and dipole moment. How you will calculate it? So as we can clearly see that the charges are equal in magnitude, so, but in they have opposite sign. So the net charge will be, if we add the both the charges, we get net charge 0. Okay, so this electric dipole moment, now we have to calculate. I have told you the formula for this, that is P is equal to, we denote it with P, and that is equal to Q into distance between the charges, and we know the distance is 30 centimeter. Okay, if we draw the diagram over here, let it be let we draw the Cartesian coordinate systems x, y and z. So we are placing one of the charge at point A and another at point B over here. So okay, so this is point B, right? This is 15 centimeter above, and this is point A. So this is total distance will be 30 centimeter, right? So you can substitute the values and calculate the answer. Now let's see the next question, which says that an electric dipole with the dipole moment of this is aligned at an angle 30 degree with the direction of uniform electric field of magnitude 5 into 10 raised to power 4 Newton per coulomb. So now we have to calculate the magnitude of torque acting on the dipole. So we have seen its formula. Torque on the dipole is P cross E. Okay, so P cross E is the formula, and we are directly given the dipole moment, which is 4 into 10 raised to power minus 9, and also we are given the electric field. So we can write it as PE sine theta, and theta also we are given that it is inclined at an angle 30 degree with the direction of electric field. So if we have to see with the help of diagram, so this is the electric field suppose, and this is the dipole, minus q plus q, and let it be angle theta equals to 30 degrees. So this is the configuration, and now you can use this formula and you can get the answer. So this is a hint for this question, so you can try these questions on your own. I'm giving you the hints. Okay, so next question is, a polythene piece rubbed with the wool is found to have a negative charge of this. Okay, now you have to estimate the number of electrons transferred. So again we'll apply the formula, that is q equals to Ne. So we have to calculate the number of electrons transferred when the polythene piece is rubbed with wool. So we are given the charge and we can substitute the value and get the value of N. And now they are asking, is there a transfer of mass from wool to the polythene? So if you think that mass is transferred or not, now the number of electrons are transferred. So if we say that electron has a mass of 9.1 into 10 raised to power minus 31, right? So this is the mass of electron. Now if we have to calculate the mass, the total mass which is transferred, so the total mass transferred will be writing it m equals to n number of electrons transferred into mass of one electron. So we can see that we'll get some amount of mass which is getting transferred. So on calculating you can get the particular number. Okay, so now let's move to the next question, which says that two insulated charged copper spheres A and B have their centers separated by a distance of 50 centimeter. So we have two copper spheres A and B, so they are separated by the distance from their centers, that is 50 centimeter. Now we have to calculate what is the force of repulsion if the charge on each is this much. So both are having some positive amount of charge which is given, and you have to find again the electrostatic force of repulsion. So now whether we can apply Coulomb's law here, since it was for only point charges, think for a while. And then they are saying that the radius of A and B are negligible. Okay, so we are having the separation. Now you will get your answer from this last line only, that the radius is negligible compared to the distance. So they have considered again the point charge only. It was just to confuse you whether you can apply Coulomb's law or not. Okay, so you can again apply F equals to K Q1 Q2 upon R square. You are given everything and you can substitute the values in terms of SI unit. I am mentioning it again. Keep in mind the units. Okay, so let's move to the next question. What is the force of repulsion if each sphere is charged double the above amount and the distance between them is halved? So they are asking what will happen to the force if both the spheres are getting doubled, their charge is getting doubled. So if we have to see the proportionality, so directly we can see proportionality that first charge will also be 2q1 and the second will also be 2q2 while the distance is getting halved. So the final distance, now the new distance will be r by 2 the whole square. So now you can see that force of repulsion is remaining same as earlier or it is getting changed. So if we see that it is getting 2 2s are 4, which goes to the numerator, so it is getting 16 times the original force. Okay, so the force of repulsion gets changed. Now the next question is, this figure shows the track of three charges. Okay, so three charged particles in the uniform electrostatic field. give the signs of the three charges. So we are having 1, 2, 3 charges, and we have to tell the sign which particle has the highest charge to mass ratio. This also we have to tell. So we can see that the first charge is getting towards attracted towards the positive charge, so it should be a negative charge, right? So the first and the second charges are negative, since they both are getting attracted towards the positive side of the electric field. Okay, while the third is the positive charge, right? So we can easily understand the sign of all the three charges. And now they are asking which particle has the highest charge to mass ratios, that is q by m ratio we have to calculate. So if we just apply the logic without calculating it, we can say that the amount of deflection in all three, we can see that the third charge is getting most deflected. Okay, so it is deflected in this direction while they are getting slightly deflected, and it is negligibly deflected. Okay, so the third charge is getting most deflected, which means that if we talk about the mass which is heavier, so heavy, if we apply, let me give you example. Suppose if I have two masses m1 and m2, so force is applied equally on both the masses. So if let the m1 mass be the lighter, okay, so m1, this is this case, okay, so the force is same, so it will get most deflected. So lighter one is getting most deflected. We can say that deflection is depending upon the is inversely proportional to mass. So now the third charge is most deflected, means it has higher charge to mass ratio. Since we can also say that charge to mass ratio, if we see the expression, it again the mass is at the denominator side. Okay, so this could be one of the explanation, right? Now let's move to the next question, which says that consider a uniform electric field. So we are given some electric field, and what is the flux of this field through the square of 10 centimeter on the side whose plane is parallel to the YZ plane. So we have a plane which is parallel to YZ plane, and you have to calculate the flux through the square. So we know the value of flux, formula of flux, which is equal to E dot A. Okay, so E vector dot A vector. So we are given the electric field in I cap, and we can say that now we are given this plane to be YZ plane. So the area vector for this YZ plane will be outward normal. Okay, let me draw this normal more clearly. It would be understood easily. So this is the YZ plane. Suppose this is the plane which we are given. So this is the x-axis. Now the outward normal will also be in the x-axis, that is in the I cap direction. So I cap dot I cap will be 1. Okay, so you will get some value of flux when we substitute the value of this electric field, and area is 10 centimeters, 100 centimeters square. Okay, now what will be the flux through the same square if the normal to the plane makes an angle 60° with the x-axis? Now we have inclined the plane. If the plane is inclined, so our normal will also be inclined, and it is inclined at an angle 60°. So we'll be applying the same formula, just now we'll write EA cos 60. Okay, so again you will substitute the values and you will get the answer. Now what is the net flux of the uniform electric field of this above question through the cube of the side 20 centimeter oriented so that its faces are parallel to the coordinate axis? So now instead of square we are given the cube, and we are asked to find the flux, and we are given the same electric field. So if we draw the cube over here and we see that the sides are oriented so that its faces are parallel to the coordinate planes. Okay, so the faces are parallel. So now we have to find the net flux. For the net flux, either you can calculate flux through the each face, right? You can calculate for all the 6 faces individually, and 3 you will easily get to be 0, since the angle between the electric field and area vector will be 90 degree, and rest you can calculate, you will get the answer. But we can also apply the concept that the net flux entering through the closed surface is equal to the leaving through the closed surface, flux leaving through the closed surface. So if the amount of flux entering is equal to the amount of flux leaving, we can say that the net flux is 0, right? So we can directly write the next net flux will be. Moving to the next question, the question says careful measurement of the electric field at the surface of the black box indicates that the net outward flux through the surface of the box is given this much. So we are having a black box, and through the box the outward flux is something, they have given the value of phi. So what is the net charge inside the box? We have to calculate the value of q enclosed inside the box. Now it is a closed object, so we can definitely apply Gauss law, which states that charge upon epsilon naught. So we just need to substitute the value of phi and cross multiply it in order to get the net charge. Okay, so the next part is, if the net outward flux through the surface of the box were 0, so could you conclude that there were no charges inside the box? Now they are saying that assume that the net flux which is outward, that is 0. So what can we say from that? Can we say that there are no charges? Because if there are no charges, then only flux will be 0. Is it possible? So we can see that in our previous example also we have discussed that amount of flux entering is equal to amount of flux leaving. So there is conservation of flux. So in that case also our net flux is assumed to be 0. So we cannot say that the flux is 0 only if the charges are not present. So it may be probably they may be present or absent. Okay, so that is not the final conclusion. Now let's move to the next question, which says that a point charge 10 microcoulomb is at the distance of 5 centimeter directly above the center of the square of side 10 centimeter. So we are having a square, and at this 5 centimeter distance we are having a plus 10 microcoulomb charge. What is the magnitude of the flux through the square? So now we are not given with the closed object, so we can't apply Gauss law, or we can apply. We have to check. Just if I say that if I close the charge, since we need the charge to be enclosed in a box, or the shape should be closed. So if I enclose it and then I apply the Gauss law, then we can find the value, okay, of the flux. So what I'll do over here is, since we are given a square and a charge is placed above it, okay, so I should enclose the charge. Let me enclose the charge by making it a cube. So in this way I have enclosed my charge, right? So this is the side of the square, okay. So we are given with this one face of the cube. Now we have to calculate the flux. So now the charge is enclosed and the equal amount of flux will be passing through all the 6 surfaces. So we are having one surface over here, so some amount of flux is passing through this side, and similarly through the rest 5 surfaces. Now we can say that the net flux will be equal to charge upon 6 epsilon naught for one phase. Okay, for each phase the flux will be this much. Now we can easily apply the Gauss law. Okay, so we have we have the value of point charge, that is 10 microcoulomb, and that will be 10 into 10 raised to power minus 6 upon 6 into epsilon naught value we know 8.85 into 10 raised to power minus 12. So the distances and the side of the square are given just to confuse you, so we can easily find the flux value from here. Just you need to perform some calculation, okay, and you will get your answer. Now let's move to the next question, which says that a point charge of 2 microcoulomb is at the center of the cubic Gaussian surface 9 centimeter on the edge. What is the net flux through the surface? Now we are given a cube and the point charge is placed at the center. So the charge is enclosed inside the cube. So we can easily apply the Gauss law in order to find the flux, right? So we can apply the Gauss law, that is charge upon epsilon naught. So just substitute the value of charge, again you will get the answer. Now the point charge causes electric flux of this much amount to pass through a spherical Gaussian surface of radius centered on the charge. If the radius of the Gaussian surface were doubled, how much flux would pass through the surface? So I have told you this in the lecture also, that flux which is passing through a sphere, suppose we are having a sphere which is of radius, we are given 10 centimeter. Okay, so if I increase the radius, now the charge due to which the flux was flowing, let the field lines be moving outward in this way. Okay, so the same amount of lines will be passing through the radius of 20 centimeter as we increased the radius. Okay, so now the flux will be same through both the spheres, right? Now they are asking what is the value of point charge. So you are given the value of flux, again you can apply the Gauss law, that is flux equals to charge upon epsilon naught. So again you have to apply the same concept. Now the next question is a conducting sphere. Read it carefully. This is a conducting sphere of radius 10 centimeter has an unknown charge. If the electric field 20 centimeter from the center of the sphere is this and points radially inward, so we can guess that our situation is something like this. We have a conducting sphere of radius 10 centimeter and it has a unknown charge. Since we are not given the unknown charge, but in the next line we can guess that since the electric field is pointing inwards, now we can say that the charge can be negative on the conducting sphere. So we have to now find what is the net charge on the sphere. So net charge we can calculate, we can apply Gauss law, that is E dot dA is equal to charge upon epsilon naught. We did it in our lectures, right, where we concluded that this conducting sphere also acts as a point charge, since we get the same expression, that is equal to E equal to kq by r square. Just we need to substitute the values. We are given electric field and this what else we are given, that is we are given distance, that is 20 centimeter from the center of the sphere. So we can apply the value of r, that is 20 centimeter. Okay, so convert it into meters, right? Now we'll get q from here. Okay, let's move to the next question. Now we have a uniformly charged conducting sphere of 2.4 meter diameter has a surface charge density of this. So again we have a conducting sphere and it has some surface charge density. Find the charge on the sphere. Now how can we calculate charge from the surface charge? We know the formula of surface charge density, which is equal to sigma equals to charge per unit area. Okay, so we are given the charge density and we are also given the diameter, so we can apply the formula of the sphere for the area of the sphere, that is 4 pi r square. You just need to put the value of this radius over here and perform the calculation, which will give you the value of the charge on the sphere. And for the total flux, which is asked in the next part, leaving the surface, we can again apply the Gauss law. Okay, that is flux equals to charge upon epsilon naught. I hope you remember the procedure where we were applying the Gaussian surfaces and then we were performing all the methods stepwise. We did it, right? So you can find the flux from this Gauss law. Okay, now let's move to the next question, which says that an infinite line charge produces a field of this much at a distance of 2 centimeter. So now you have to calculate the linear charge density. So this also we have done in our previous lecture, where we have seen a line or the infinite wire where the charge was distributed on the surface of the wire, and we have calculated that electric field due to the wire by applying the Gaussian surface of cylindrical in nature. Okay, that was cylindrical in nature. Like this, we have found the electric field, which was lambda upon 2 pi epsilon naught into r. So now we are given the field and we are also given the distance. From there we can find the value of lambda, and this is only we need to find the linear charge density, right? So now let's do the last question of the exercise, which says that two large thin metal plates are parallel and close to each other. So we are having two metal plates which are close to each other. On their inner faces, the plates have surface charge densities of the opposite signs and of the magnitude this much. What is the electric field in the outer region of the first plate and in the outer region of the second plate and between the plates? So we are given the metal plate. Now first we have to analyze the situation. So they have said two large thin metal plates. So let me have two metal plates. Okay, and they are parallel and close to each other. So for understanding, I am making it at some distance, but they are kept close to each other. On their inner surfaces, the plates have the surface charge densities of the opposite signs and of the magnitude this. So if I suppose that plate 1, let it be plate 1 and let it be plate number 2. So plate 1 has a positive charge on its inner side. Now we have to see that the plate 2 must be having negative charge on its inner side. Okay, since they are saying that the plates have opposite charges, opposite signs, right? So what is the electric field? First we have to calculate on the outer region of the first plate. Means let it be point P over here. So we have to find, this is our first region where we have to find the electric field, and in the outer region of the second plate. So this is the second region where we have to find, and in between the plates, which is the third part which we need to solve it. Okay, so we have to check the electric field at the point A in this first region. Now for the first region, region 1, we can see the electric field will be, the electric field for due to the first plate will be in this direction. Let me say it E1. Okay, and the electric field due to the second plate will be in its inward direction, so it will be towards the plate 2. Okay, so this will be E2. So the net electric field, if we need to find, that is E1 minus E2. We'll write it in this way. So we know that the electric field due to the metal sheet we have calculated, that is equal to sigma upon 2 epsilon naught. We need to substitute the values here. So for the first we have to write sigma upon 2 epsilon naught, and again we have to write sigma upon 2 epsilon naught, since we are mentioned that they both are having the same magnitude. So the magnitude is same for both the faces. Okay, so now you have to keep in mind, for the net electric field it was in such a way, the net electric field which we usually calculate is E1 plus E2. But here what we see that the electric field 2 has the direction opposite to the 1. So for the opposite direction the sign will change to minus from plus. So that's why we need not to substitute the value of minus again. Okay, so this is only due to the opposite direction. Now the magnitudes are equal, so the net electric field in region 1 will be 0. Okay, so now let's find the electric field at point P. Let's suppose now our point P is over here. Okay, so if we find the electric field in region 2 for the plate 1, so the electric field due to the plate 1 will be in this direction. We can write it as E1, and due to the plate 2 will be in this direction. So again we'll get the net electric field to be 0 in the second region. For the third region, let us say now we have a point P over here. So just where they are saying to find the electric field, just put the point there and find the directions of the electric field. Now we can see that for the plate 1 the electric field will be in this direction, which will be E1, and for the plate 2 again it will be in the same direction of E1, so it will be E2. So for the third region we can say that the net electric field is, both are having same direction, E1 plus E2, so it will be sigma upon 2 epsilon naught plus sigma upon 2 epsilon naught. We'll get sigma upon epsilon naught, right? Now we are given the value of sigma. The magnitude given is 17 into 10 raised to power minus 22. So we'll substitute the value 17 into 10 raised to power minus 22, and upon epsilon naught you can get the net electric field in the third region. So these were some questions of the NCERT exercise. Now you must have got the idea and the clarity of the concepts. You just need to keep in mind the methods which we are using in each question. So for this type of question we are using the method is, our first step is we have to identify where is the P point. Okay, so that is, we have to read the question carefully, just see where we have to check the electric field, either in first region, second region, third region. You have to see it, and then you have to see the value of the electric field, and then the signs of the charges on the plates, and just check the direction of the electric field. It's just this much of work, and rest is your mathematics. So you have method for each question which will help to make your concept strong, right? So try out these questions on your own, and if you need any help then you can let me know. Okay, so we'll study till here in this lecture, and we'll continue next chapter of class 12th in the next lecture. Okay, so till then, thank you, all the best.